Hello, this is Dr. Muhammad, and this is another video under dynamics of structures. And today I'm going to talk about forced vibration. Still, we are under this main topic, which is related to forced vibration. And today I'm going to talk about response to arbitrary general dynamic loading, which we started 2 videos before. And today I'm going to talk about the application using triangular loading. So it is considered to be a specific case related to the arbitrary general dynamic loading. Last time it was part 1, today it is part 2, and by this we are going to finish the single degree of freedom system, and we are going to start after that in multi-degree of freedom system topic. Okay, so we can start directly to give some hints and introduction to this topic. Okay, so let's start with the introduction, where I'm going to give some hints, or we can call it introduction to this topic. There are some things, there is something that I want to highlight before starting or before the beginning of this video, that if we have ground excitation, or of course, if we have a ground excitation that is going to be for earthquake, for example, something like this. In this case, we are not knowing the function. There is no like function, or there is the function pattern is not known. It is not, for example, it is not triangular, or it is not rectangular. So we call this, it is unknown function pattern, not known function. It is something similar to the earthquake, for example. So if we have a ground excitation, okay, if the load of the ground excitation is not known function, or if the system is nonlinear, okay, the system itself is nonlinear. I mean that the single degree of freedom system is not linear. We are talking about linear systems up till now, okay? But in the future, maybe, or if we could find time, we're going to talk about nonlinear system. But now, if we are dealing with nonlinear system, or if we have a ground excitation that is not having a known function pattern, in this case we need to resort to numerical solutions, okay, or numerical solution methods should be used in this case. Okay. As I said many times, this is mainly because we are going to solve differential equations, and unless that the load pattern is known for us, we are not going to find a closed form solution. This means that we need to go to the time-stepping methods or numerical solutions for the solution of the differential equation. Okay, so this is an important hint. I'd like to keep it in our mind before going into this topic. Another thing is there are many methods found in literature dealing with numerical methods, and this is true actually. This course is related to dynamics or structural dynamics. It's not related to numerical analysis. So this is why I'm not going to place emphasis, and I'm not going to explain in detail what are the numerical methods that we should use for the solution of the dynamic response, because already, as I said, there is a wealth of knowledge found in literature, and you can find many sources that is going to provide you with a great deal of knowledge regarding numerical methods and how to solve. Okay, for example, you can refer to the textbook, our textbook, which is Chopra book. It is in the 3rd edition, chapter 5. You are going to find the numerical time-stepping methods. I'm going to give like one slide about this, and maybe in the next slide I'm going to talk about this. What are the main types of it, and what are the important things that we should keep in our mind related to numerical time-stepping methods. Okay, so numerical time-stepping methods for integration of differential equations is commonly used. We call it time-stepping method or numerical time-stepping method. Very famous. You are going to find that it's a common way for many researchers and engineers who are using it. Okay. Okay, and after that we are going to find, yes, I mentioned already about that the wealth of knowledge that there is a wealth of knowledge exists on numerical methods, but I'd like to give here something or like give a hint here. So do not distract yourself with too many methods of numerical methods, because as I said, it is a well-established knowledge and a great deal of wealth out there in literature. So you can find one or two sources and you can study about them, and also are going to find that it's mostly this numerical methods, it's time consuming. So try to understand one or two methods enough for you for dynamic analysis, and you are going to understand them once in a lifetime and then keep it, because this is where the software is going to help you a lot. Okay, this is what goes inside the black box. So you need to like understand that how numerical methods in general are working, and after that leave this part to the software that you are using. It is going to do it better than you and more accurate, and we need to think about what should we understand from dynamic analysis, not going into the details of numerical methods. Okay, and you're going to find that in the near future, I think that there are soft computing methods are going to overtake the old traditional numerical methods, and you're going to find that using artificial intelligence or machine learning technique or soft computation techniques, you're going to find that you're not going to spend the time that you used to spend whenever that you were making or solving using numerical methods. So take care of this and keep it in your mind. Only understand it once and then keep it for the software to do it for you. Okay, commonly direct integration method commonly used in general purpose programs. For example, in SAP 2000, you are going to find they are using direct integration method. Okay. And in the next slide, I'm going to some hints about common numerical methods used for evaluation of dynamic response. Okay, are given in the next slide. Okay, so let's go to the next slide. As I said, I'm going to talk about this, which is the types of numerical methods. Only one slide. I'm not going to give a lot of time for it. It's only for us to understand. For us to understand more about numerical methods. Okay. In general, we have the type of time stepping. As I said, time stepping methods are the most common ones. So commonly we are having 3 different types of time stepping procedures. Okay, so these are, first, let's have it like this. Okay, so first we have methods based on interpolation of the excitation function. So we're going to find that we have the function, and we are going to like interpolation between 2 time steps. For example, we are going to interpolate between them, and we are going to solve our equation of motion, or we're going to solve the differential equation here. So this is the first type, which is related to interpolation of the excitation function. Another method based on finite difference, okay, expressions of velocity and acceleration. Okay, so we are going to use, or the other method is related to finite difference expressions of velocity and acceleration. And the third one is, or the third category is related to methods based on assumed variation of acceleration. Okay, variation of acceleration. So here, this is the first type is related to interpolation of the excitation function itself. The second, it is related to the finite difference for velocity and acceleration. And the third one is related to the variation of acceleration only. Okay, these are the 3 different types or methods that you're going to have. Okay, and then what should we take care of when we are dealing with the numerical or the time stepping methods? Okay, So in general, whenever that we are dealing with time stepping methods, always we are going to have steps from point I to point I plus 1 if we are going to have, for example, something like this. And we are having like the slices here, we have like I and I plus 1 and so on and so forth. So it is not an exact procedure. So it is not going to give us the exact solution. Okay. Many approximate procedures are possible that are implemented numerically. The three important requirements for a numerical procedure are, so we are like putting some guidelines from outside, or we are putting like some guidance for whatever the type of the numerical method that we're going to use. Okay, so first of all, we need to keep in our mind that it is not an exact procedure. This is number one. This means that we are having some approximation. Okay, it is not exact procedure because we are going to have some approximation. As long as we are going to use some approximate methods, we need to keep in our mind three important criteria for this numerical method. First of all, we want to guarantee the convergence. The second is the stability, and third is accuracy. So you need to keep in mind these three things. So convergence means that as the time step decreases, the numerical solution should approach the exact solution, okay, at the end of it, okay, at the end. Okay, so this is the first thing. This is what we call it, the convergence, okay. And number two, stability. The numerical solution should be stable in presence of numerical round of errors. That's very, this is a main issue, okay, for those who are concerned with numerical solutions. Stability is an issue, especially for the round of errors. The third one is the accuracy. So the numerical procedure should provide results that are close enough to the exact solution. We need to maintain some minimum accuracy for our procedure, okay. So these are the important things that we need to keep in our mind whenever that we are dealing with the time stepping methods. Okay, now let's go to the next part, which is related to the triangular load. Again, why we choose this triangular load? Because if you remember, last time I was talking about different types of loading. We have triangular loading. If we have, like, for example, t and f of t here, the function is something like this, and we said that it has something like function that is known function. We can put a pattern. We can put an equation for it, whether it is triangle or rectangular, for example. These kind of forces, or we can have something like this, okay, which is having the maximum here and goes up here and then goes down here. This is known function patterns that we can develop the equation, or at least we know the equation, how we can describe the force by an equation. Based on that, we are going to find at the end, we're going to have like two phases here. One phase, we call it, this is the forced phase. For example, it will be, the response will be like this, and after that maybe the free response phase. But at the end, we are going to find something we can use to obtain what we call it the closed formula or closed form solution at the end. So we are having different types of loading. Triangular loading, one of them, and rectangular loading is going to be also one of them. We're going to go into the details of triangular loading, and then we're going to have an example. In a similar way, we're going to apply on rectangular loading. Okay, now let's go and see more about the triangular loading. And the triangular load, we are going to talk today about this in particular, okay? As an application to arbitrary loading that can be solved analytically. The point is why we choose this triangular loading, or if we choose, for example, rectangular loading. Why? Because we are going to show to you that it can be solved analytically. So we're going to make some some manipulation of our equation, and at the end we're going to obtain a closed form solution using our analytical skills, okay, for the solution. Okay, that's the point. Okay, from previous lecture we learned. Let's go now to what we have studied last time and remind and refresh our memory regarding it. Okay, so regarding this, we have mentioned before that if we have initial conditions, okay, the general solution, if we have initial conditions, U node and V node, means that U node does not equal to 1 and V node does not, does not equal to 0, and V node does not equal to 0. Okay, so in this case we are going to put the values of U node and V node, and it is going to be reflected on the equation of motion that we have. This equation of motion, the derivation of it, I think that if you want, you can revisit the previous video and you're going to find it. Okay, and we are going to title it with equation 1. So the response here is, or U of t means that the response or the dynamic response at any time t equals to 2 parts. So the first part is related to free vibration part, and the second is the forced vibration part. Okay, so we have 2 parts here. 2 parts here. So for the forced vibration part, if we want to start with this, so the forced vibration part, you're going to find the main parameters used here is related to from 0, there is an integration from 0 to t, means that it is limited integration based on the function that we are having, which is f of tau here. And then we are having a sinusoidal function, sine omega t minus tau, where tau, it is the time period before the start. Okay, d tau, this is the parameter, still it's time also, and multiplied by constant, which is the mass, 1 over mass, and omega, the circular frequency. So this is related to the forced vibration part. This is the part that is going, if we are talking about any type of loading that is known, for example here, this is triangular loading, this part, what we call it, the forced vibration part. After that, the system is going to respond freely. So we call this part to be free vibration part. And it is going to be added, or we are going to represent it in our equation by this term, which you can see here. It has U node and V node. Remember that well. They are the initial conditions, the initial displacement and initial velocity, right? Because as we said, we are talking about other initial conditions that we have when we derive this equation. We said there are 2 cases. One, or the first case, where that the initial conditions, or we were at rest conditions, and the other type or other case where that we have U node does not equal to 0 and V node does not equal to 0. And we found that in this general equation, the part that is related to the force, the term that is related to the force, we couldn't find any effect or impact of U node and V node. We didn't find any kind of relation to the initial conditions. However, when we look to the free vibration part, we found that we have U node and V node. So this means that our initial condition is always going to affect the free vibration part, which is going to be starting from here. Okay. However, in the forced vibration part, initial condition is not going to affect us here. Okay. Another thing that we have cosine and sine. This means that we have sinusoidal function. Addition of 2 sinusoidal function means that we are expecting something to be wavy, something like this. Okay, so this is the understanding of the equation. Okay, and this is what we have we already have explained about it before. Okay. Now let's go and let's consider the system that we are dealing with for today. Now let's consider that we are having, let's consider a system represented by the undamped, so we are dealing with the undamped system. Take care, okay? We're talking about undamped system. Damping is zero. Undamped system or oscillator. Initially at rest. Initially at rest means that we have U node equal to V node equal to 0, right? Subjected to a force f of t. This is the force pattern force function that we're going to talk about as shown below. So actually this force that we're talking about, it is going to be, as you can see here, the relation between t and f of t, it is triangle. And triangle means that we are having a line here, so we can derive the equation of this function. Okay? So first of all, we are going to look to this function as two parts or two phases. The first phase is going to be from t equal to 0 here, okay, 0, till the end of the force, because the force pattern, which is this line, the triangular pattern of this force, is going to end at a point of time called td. Okay, this is what we call it. We are going to call it phase 1. And we are going to call it, as I said before, it is the forced vibration phase. The forced vibration phase. The second phase is going to be, as you can see it here, this is the second phase, which is going to be starting from TD on. Okay, this is what we call it phase 2, and it is the free vibration part. The free vibration part. Okay, then we are going to write the equation of the force first. Okay, so if we look to the force, we are going to find that it has at t equals 0, this force magnitude was F node, and at t equal to TD, this force magnitude found to be 0. Then we need to put a function for it. Let's start from the basics in order to put the function for this line. We are going to start with phase 1, which is where that we have t less than td. This is the domain here, from 0 to 2td. So this is phase 1, the forced vibration part. Okay, if we look to this function, we are going to find, or this line, we can describe this line through its slope. So the slope of the force function is going to be, the slope in general for this line is going to be F node, which is, we can call it the opposite, over the adjacent, right? So in this case, we are going to put this as the, so this slope equals to F node over TD, and it equals to the opposite, which is F node on the vertical axis, over the adjacent here, which is, as we can see, which is TD. I was writing it the hypotenuse, but actually it's not right. Hypotenuse, it is going to give us this line, but we are talking about the slope, which is tan this angle. Okay, and then we are going to equate it, this opposite is going to equal by the similarity of triangles. So we are going to find this small triangle here is similar to the large triangle here, right? So if we say that the slope, if we say this is the angle that we're talking about, it is similar to this angle. If we, both of them, for example, we call them theta. Okay, so in this case, theta here equal F node over TD, and theta here, which is similar to this theta in the larger triangle, is going to equal to this this part, or this portion here. This portion is we are saying that this is any point or the value of the force at any point tau, where this tau between 0 and td. Okay, this is what we are going to be. Let's remove everything here. So we have f of tau at time equal to tau between 0 and t of d. Okay, this is the function which is going to be variable according to the location of this t on this axis. Okay, so in this case we are going to say that f node minus f of tau, which is the value of the function at this particular time, which is tau, over td. Okay, td, as we said, sorry again, this is the not the hypotenuse, as I said, it is the adjacent. Okay, so remember, put it in your note. Okay, so this is based on the triangle's similarity. This is based on the triangular similarity. So we're going to look to this. We have f of tau here, and we have f node and td in the right hand side. Then we are going to rearrange this equation and putting f of tau to be on the left hand side, and put everything in the right hand side. So we are going to make this. Okay, so we are going to rearrange. So we're going to rearrange here. So as you can see here, f of tau is going to be in the left hand side, which is here, this f of tau, and it equals to f node times 1 minus tau over td. Okay, this is our equation. Okay, this is what we call it the forcing function, or the force function. This is the force function. Okay, this means that we can represent the value of the force at any time based on the time itself, tau, and the duration of the force, and f node, which is the maximum value of the force, if we are talking about triangular loading. Okay, so this is the forcing function. Okay, this is the forcing function that we are going to use from now on. Okay, and in the beginning we assumed at rest initial conditions, means that we are having u node equal to v node equal to 0. Okay, so the system was at rest when we started to trigger our force. It was at rest. So we are going to find that our initial conditions, u node and v node, is going to be 0. This means that this takes us back to, if we're going to this equation here. So in our equation we have this term, the first term, u node and v node, it is going to be 0, right? This term, this one here, it is going to be u node, and v node, it is going to be 0, right? So this term is going to be, or vanish, going to vanish. Based on that, if we're going to substitute in equation 1, okay, in our equation 1, we are going to find that this term only is going to work for us, and the forced vibration phase. So after substitution into equation 1, then we are going to integrate. We're going to make integration by parts in order to get the integration, because we have an integration here, if you remember, from 0 to t, limited integration. So based on that, we are going to use integration by parts. Integration by parts. Okay. So this means that we are going to have the integration by parts, and based on that, we are going to find the final equation, or the response of our system is going to be f node over k times 1 minus cosine omega t plus f node over k td sine omega t over omega minus t. And this is, we are going to call it equation number 2. equation number 2. Remember that this equation is describing for us how the system is going to be responding in the or during the first phase, which is the phase of the application of the force. Okay, so it equals to F node. Let's go and understand every term here. F node means that it's the maximum magnitude of the force. K, it is the stiffness of the system. Cosine omega t, it's sinusoidal function related to the circular frequency of the system. Then we have again F node over K. It is, if you remember F node over K from the previous video, we said that it is the maximum static response, the maximum load over the stiffness of the system. This gives us the maximum static response. And here there is TD, which is the duration of the force. Okay, it is TD, horizontal one, if we have the force here. So the horizontal distance here, this distance is TD. And then sine omega t over omega minus t. So everything here is known for us. And as you can see, we do not have any initial conditions or something like this, because already we said that they are 0. Okay, so this is equation number 2, which is going to represent for us the dynamic response of the system during the first phase. This equation can be rewritten using the deformation response factor. Do you remember the deformation response factor? We mentioned about it last video. Please, if you didn't watch the previous video, stop this video and go back, and you are going to understand what is the meaning of the deformation response factor. And in short, this deformation response factor, we call it RD, or we give it this this abbreviation RD, and it equals to U of t, which is the dynamic response of the system over the maximum static response of the same system. Okay, so as we said, this is RD, the ratio between the dynamic response at any time of the system over the maximum static response of the system. What is the maximum static response here? If you remember, we mentioned this also last time. It is going to be F node over K, right? It is the maximum force over the stiffness of the system itself, over the stiffness of the system itself. Okay, now let's go and try to give or represent this equation in terms of the RD. Okay, sometimes it is useful for us to use RD instead of putting only U of t, because we are interested in, as designers, we are interested in the maximum value always. So we are not interested in what is the specific response at every time. Okay, maybe for some research point of view, or from research point of view, we might be interested in specific response at specific time. But in general, if we are in the design stage and we want to know what will happen for a system that is being excited by triangular load with a duration of TD, for example, and having the maximum magnitude of this applied load to be F node. This is what we want to know. What is the maximum value for the response? Whenever we think about maximum value, then always we should think about deformation response factor, RD, because again, it is going to give to us what is the relation between our dynamic response to our maximum static response. This is an important quantity or an important information about our system and the load that is being applied on our system. So based on that, instead of describing the system with the equation having the dynamic response on the left hand side, we are going to represent the same equation in a different way using RD. Still, we are talking about phase 1, of course, which is the forced vibration. So in this case, we are going to divide this equation, equation 2, by F node over K. As I said before, remember that the maximum static response, which equals to F node over K, if we use it and divide the equation 2 by this U static node, so we are going to find that this term and this term, they are going to disappear, right? They are going to be divided by the same value, then it will be 1 here, and here we are going to have U static node, which is RD, right? So we put it like this. This is RD here, okay? So this is the relation between, again, U of t, the dynamic response at any time, over U static node. What is the meaning of U static node? Static means that it is static force. Node means that maximum. So we have this relation. Dynamic response at any time over the maximum static response that we have. Then this equation, which is equation 2, let's clean everything here. This equation, which is equation 2, is going to be represented by this equation, which is in terms of RD. We're going to find that F node over K here, F node over K here will be disappear, and then we're going to remain with the remaining part, which is 1 minus cosine omega t plus sine omega t over omega td minus t over td. Remember, we're talking about phase 1. This means that we are in this place, which is t less than td. T less than td. Okay, so this is the equation, and this is how we are dealing with, or how we are going to represent our system when we are in phase 1, this phase. Okay, we are talking about this phase now. Okay, we're talking about phase 1. Okay. The next is going to be phase 2. How we are going to deal with phase 2? We need to find the equation of motion that is going to describe this phase, and we are going to put it also in terms of RD, as we have done in phase 1. Okay, now let's go and see what or how we can deal with the problem in phase 2. Okay, this is phase 2 here, where that we have t larger than or equal to td. Okay, only the free vibration part of equation 1 will be used. This is equation 1, as we have mentioned before. We have two parts again. This is the free vibration and forced vibration. So the free vibration part is going to work for us. This part, which is the forced vibration, is not going to be there. So this part is going to be not going to be there. Why? Because f of t is 0. So everything is going to be 0 for us. Okay, from here it is everything is going to be 0. After td, everything is going to be 0 here. So we have only this part. Okay, we have only this part, which is the first part, or the free vibration part. U node and V node is there always for us, right? Now, for the free vibration part, we need to think about the initial conditions. Even that the system started at rest as we have assumed in the beginning, but the start of this free vibration part is from here, which is at the end of the forced vibration. The question is, does this mean that at rest condition for the free vibration part? The answer is no, because at the end of the forced vibration, which is the start or the beginning of the free vibration, at this particular point, U node and V node, they do not, both of them do not equal to 0, of course. We have something, the system was under this forced phase, This means that at the end of it, there is value for the displacement and for the velocity, right? And this is the key that we're going to use to solve the free vibration part. Okay. So now for us, we understood that we are not going to use this part, okay? And we are going to use this part only for the representation of the force. Well, our equation in this case is going to be u of t. This is the dynamic response at any time. This time is going to be after TD. So after TD means that here, this point is going to be t minus TD, right? Because we have from here to here, this is TD. And at any point here, which is t, it is going to be t minus TD. Then whatever that is going to be inside the function or the sinusoidal function, whether the sine or cosine, and instead of using t, it is going to be exactly t minus TD. Okay, so now we understand why we put this t minus TD. Okay, this is number one. Number two, u node and v node, they are not going to be zero, as we said. Why? What is the reason? Not because the initial conditions at the beginning, before the force vibration, it was zero. We said that it at rest initial condition. But actually, our case, we started from here at the end of the forced vibration. Then v node, u node are going to have values, right? Okay. Now, from equation 2, let's clean everything here. From equation 2, we can obtain u node and v node. Okay, we can obtain u node and v node. Okay, because we are having everything. If we have the equation for the response, we can derive it and get v node, which is u dot, and then we can put t instead of t, we can put it equal to TD, right? This would give us the initial conditions at the end of the forced vibration phase and the beginning of the free vibration phase. Okay, so we are going to have where's equation 2 here? This is equation 2. We have u of t equal to f node over k and so on. This is again, this is related to what? Phase 1. This is phase 1. Okay, remember, we are going to use it, but instead of t, okay, t here, we're going to use the TD. Okay, and in the same time, this is going to give us u node, and then we're going to derive it, okay, first derivative in order to get u dot, okay, which is going to be node at this part, which is going to be v node, which is going to be u dot of TD, and this is going to be u node, okay, of TD. So we're going to derive this, we're going to have the first derivative of this equation, and we are going to obtain the value, or we are going to substitute in order to get u node and v node. By putting t instead of t, it is going to be TD, right? Okay, let's erase here and go back to our phase 2. Okay, so now from equation 2, we have u node, now this is u node for us, equal to u of TD. And instead of t, it is going to be TD. We are going to have the first part only. The second part, which is related to the force, is not there because we are, as I said, here there is no force. So the second part, the forced vibration part in the equation, it is going to vanish. So we're going to have f node over k times 1 minus cosine omega, exactly TD here, not t, sine omega td, and this is td already in the equation from the beginning, and td over td. Okay, it seems that here this is 1 will cancel out this 1, and we are going to end with cosine omega td and f node over k outside of the parentheses, okay, the square brackets here. So we have sine omega td after rearrangement, omega td in the numerator, minus cosine omega td, okay, minus sine omega minus cosine omega td. Okay. Okay. So remember, Will, as I said, remember that we have here at this part, this is going to be the initial condition for us. So the initial conditions for the second phase going to be, or which is the start at t equal to td. So at this part we are going to have u node and we have v node, the new one. U node is going to be u at t of d from first phase. V node is going to be u dot of td from the first phase. Okay. 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 Now let's go and get this v node now here. So we have v node. It is going to be equal to u dot td, and it equals to f node over k. From where we got this, we have the derivation, the first derivation of equation 2, as we said. Then times omega sine omega td again, and plus cosine omega td again, over td minus 1 over td. Okay, from the first derivative of u of t, as we said, of phase 1 equation related to the phase 1. Okay. Substitute in equation 3 by u node and v node. Now we have the values of u node and v node, right? Where is equation 3? This is equation 3. Okay, we have v node, we have u node here. Okay, we have u node and v node. We know them. Then we're going to substitute in the equation. Okay, so we are going back here. Okay, so we're going to substitute. Okay, and substitute into equation 3 by u node equal to u of td and v node equal to u dot of td. We get this equation, which is u of t equals to f node over k omega td times sine omega t minus sine omega t minus td, close the parentheses, minus f node over k times cosine omega t. Okay. If we divide this equation by u static, okay, u static node, which means that f node over k, as I said many times, it is the maximum static response. So we're going to, like, this term is going to be divided by the same value, so it is going to be 1, and here it is going to be divided by u static node. Okay, this would give us what exactly? The left hand side is going to be RD, the deformation response factor. Okay, so we are going, or we will obtain RD, which is the deformation response factor in the left hand side, which is equaling to, or which equals to u of t over u static node, which means, or the right hand side is going to be 1 over omega td, and times the inside the parentheses, it is going to be the same sine omega t minus sine omega times t minus td minus cosine omega t, and this term is going to disappear after the division by the same value. Okay, this is the equation of motion in terms of RD for the system after t larger, or after td, which means that t larger than or equal to td. Okay, this is the meaning of this equation. Okay, I want to highlight again, please do not be confused. They are long equation, I know, but they are easy and simple. This is the response of the system in terms of displacement at any time t. This equation is giving to us the deformation response factor, or some people call it dynamic response factor, at, okay, not at, but we are talking about, yes, we are talking about different time because we have t here, but it is going to give us the maximum value, which is ut over the, or we are going to obtain, sorry, the ratio between this dynamic response and the maximum static response. So if this RD, for example, equals to 1, what does it mean? It means that the system dynamic response is not going to exceed the maximum static response. Okay, they are going to be equal. What is the meaning of RD equal to, for example, 0.1? This means that the dynamic response is going to be very good for us because it is going to suppress the maximum static response, and instead of being 1, it will be 0.1. It will reduce the maximum static response by 90%. But if we have RD equal to 2, for example, this is problematic for us because we are going to find our system, due to the response or the dynamic response, is going to have double the maximum static response. You understand? This is the meaning of what we are having for the RD. Okay, so now we understood. Now we obtained these two values here. We have RD for the first phase for t less than td, and we have RD for the second phase for t larger than or equal to td. Okay. Now we are going to look to the maximum deformation response factor. Remember this one, this RD, it is at any time. It is at any time. This RD at any time, because we have u of t here. It's dynamic response at any time. Dynamic, I mean deformation response factor at any time. But we are not interested, as I said, in any time. It is we are interested in the maximum. What is the maximum? So we need to go and look to the maximum. Okay, we need to go and look to the maximum. Okay, for us the maximum deformation, response factor, the maximum deformation response factor, okay, we give it this RD, okay, maximum. R means that the maximum, this is the deformation response factor. It is the ratio between dynamic and maximum static. Okay. For D means that it is displacement. Maximum means that maximum all over the time that we are considering. We should get UT maximum. What is UT maximum? It is the maximum dynamic displacement. Okay, the maximum displacement or the maximum dynamic displacement at certain time t. What is the time t for the maximum displacement? We do not know. We do not know which time exactly. What is the particular point of time that is going to give us the maximum displacement? We do not know it. Okay, this means that the maximum response. This can be obtained by equating u dot of t, which is the second derivative of the equation, by 0. From this equation we can get t maximum. That's right. We can obtain u dot, okay, u dot of t, we equate it with 0. This equation, it has t, and then equate it with the right hand side to be 0. Then we are going to obtain t equal to specific value, okay, equal to specific value, whether for the first phase or the second phase, right? This t maximum, we call it t maximum. It doesn't mean anything except that the t where the maximum response is going to happen. This is the meaning of maximum here. Okay, maximum, it doesn't mean in terms of t, because t it has nothing to do with the maximum response. I mean the value of t itself. It is related to what is the point of time that is going to give us, if we have something like this, what is the point of time that we are going to obtain t it is going to give us d maximum, for example. That's the meaning of t maximum here. Okay, it corresponds to ut maximum. Then we're going to substitute into equation 4 by t maximum to get rd maximum. Equation 4 here means that the equation that is containing rd. Okay, because we have two types of equation. If you remember, we have two types of equation, right? One equation which is u of t, okay, and the other one rd, right, for first phase and second phase. So we have like this is for the first phase, and again we are going to have the same also set, which is u of t equal to something and rd equal to something. Okay, the right hand side always contains t, right? Always contains t. So whenever I say that, we are going to get the first derivative here, which is u dot of t, and equate it to 0. Then we are going to obtain t. And then from this t, we are going to substitute here in the equation of rd. Then we can obtain the maximum dynamic response. Okay. Then substitute in equation 4 by t maximum to get rd maximum. Okay. If we draw the relation rd maximum versus td over t, t, it is the system, the natural period of the system. This relation is called the displacement response spectrum. Okay. Why we call it like this? Displacement, because we are talking about displacement, not velocity, not acceleration, up till now. So we're talking about u of t, okay? Not u dot of t and not u double dot of t, okay? So we're not talking about this. So this is the meaning of displacement. And this is response, displacement response. It is response due to dynamic effect. Spectrum means that it is like the light spectrum. In light spectrum, we can see only specific number of wavelength of light. For example, like rainbow, which means that we are having 7, for example, lights. This means that they are the elite, they are selected, they are spectrum. Spectrum means that selecting like specific elements from many elements. We have many wavelengths, right? So we are taking like the selected ones. This is the meaning of spectrum here. Okay. So let's erase here. So if we draw this relation between rd maximum and td over t, then we're going to give this graph, which is going to be very important for us. We call it displacement response spectrum. Displacement response spectrum. Okay. Let's draw this for the triangular loading. Why we are drawing this? Why we need this rd maximum versus td over t? Because if you look here, it is a little bit taking time. It is going to take time for us, right? For like making the first derivative and then equate it with 0 and then get the t maximum and then like substitute again in the rd to get rd maximum, it is like going to take time for us. So they found that for each specific loading type, we can find this easily by drawing it. How? You're going to find that, for example, we can draw the displacement response spectrum for triangular loading by putting here t, d over t, and in the vertical axis we are going to put rd maximum. Okay, rd maximum. It is going to be provided in graph. Instead of making it for in tables, for example, we put it in graphs, into a graph. So this graph, for example, it is giving to us the relation between rd maximum and td over t. Okay, let's go to any point here. What is the meaning of point 5 here? This means that the loading, which is here, if it's like td, for example, divided by the natural period of the system equals to 0.5. For example, if the system is going to have 2 seconds, then TD is going to be 1 second. In this case, we found that at 0.5, we found that the value of the dynamic or the displacement response spectrum is going to give us the value of RD maximum to be 1.2. Again, what is the meaning of 1.2? This means that the dynamic response will be higher than the maximum static response by 20% in this system. Okay, but not UT only, it is going to be UT maximum, because we are talking about the maximum here. Okay, this means that the maximum dynamic response of the system is going to be 20% larger than the maximum static response. So if you are a designer and you find TD over T 0.5, you are going to say, hey, it is not good for me to have it like this. The optimum is to obtain it 1 to be equal to be the same. For example, the maximum dynamic response equal to the maximum static response. And if you want to suppress the loading, then you are going to choose value, for example, like this value, which is 0.2. Okay, if TD divided by T equal to 0.2, it would give us maximum dynamic response factor here, RD maximum. It is going to give us, for example, 0.6. What does it mean? It means that the maximum dynamic response over the maximum static response is going to be 0.6. This means that the dynamic effect is going to reduce the maximum static effect of the force by 40%, which is 1 minus 0.6 equal to 0.4. This is 40%. Okay, you understand it? That's the meaning. That's the meaning of this chart. Well, the question now is going to be, well, if we have different loading, this is only for triangles. What if I have like rectangular, for example, loading? The answer is okay, that we have it. We are having like charts that is going to give for us different types and patterns of forces. So this is for rectangular. This is for rectangular. Okay, and for the rectangular, as you can see here, it is also similar. The horizontal is TD over T. Vertical is going to be RD, take care, maximum. What is the meaning of RD maximum? It means UT, the dynamic response, maximum, over U static response node, maximum also. Okay, that's what we have. If you look here, for example, the same. If we have 0.2, the ratio between TD and T 0.2, we're going to find that our system is going to have 1.2. This means that 1.2. This means the dynamic response is going to be higher than the static response by 20%. Okay. Okay. So I think that we have understood now what is the meaning of these graphs, and they are titled with maximum deformation response factor for undamped oscillator acted upon by triangular force, if we're talking about this graph, and rectangular force, if we are talking about the below graph. Okay, so we are going to have different graphs. Also, we might find something like this, which is like triangular load, but it is with similar and having TD like splitted or divided. And we have different types of floating. Maybe you are, instead of having something like this, maybe something like this, for example. So you are going to find different graphs. Where we can find it, you can find it in the textbook. And in last video, I have showed to you the responses of different load patterns. So please revisit the previous video for more details, about this. Okay. Now let's go to something else, which is, I think it is the time now for the example. Okay, so I think it's the best time for us to have an example in the time being. Okay, let's go and find. Okay, so this example, let's focus on it and try to find how we can solve it. And this is considered to be an application that we can find in our real practice. It is a one-story. It is a one-story building. One-story building. One story here means that it is single degree of freedom system. Okay, so it is not two-story or three-story. It's not high-rise. It's not multiple or multi-degree freedom system. So we are talking about one story. Okay, one-story building. This is as shown here. This is figure 4.6. Okay, is modeled as a 15-foot high frame with two steel columns fixed at base and a rigid beam supporting a total weight of. Okay, whenever that you read the example, you need to be to have your eyes to be open for specific key words. For example, with two steel columns fixed. The word fixed here is a key word. So the bottom here is fixed, because if it's hinged, for example, or hinged fixed, it's going to be different. Okay, the end conditions is going to be are going to be different for the columns, for example, and we need to consider this. So both of them are fixed at base, and this would make our life easier, as you are going to see. At the base and a rigid. The word rigid here is a key word. Rigid beam. What is the meaning of rigid beam? Rigid beam means that it is shear building. Means that the beam is having very large stiffness compared to the column. If we are talking about, for example, inertia here, I beam, and this is inertia of the column, this means that our I beam is much larger than I column. Okay, what this piece of information is going to provide us with? It would provide us that the mass of the single degree of freedom system is going to move, okay, in this direction, and we are going to have a 1 degree of freedom, okay, one coordinate only, that is going to be 1 degree of freedom that is going to be represented. Means that we are dealing with SDF, single degree of freedom system. Okay, there is no rotation is going to be there. The relation between the beam and the column, it is going to be something like this. This is going to be always 90 degree. Okay, so that is the meaning of the word rigid here. Take care of this. Rigid beam supporting a total weight of means that we're talking about the mass. If we know the gravitational acceleration, then we can obtain our mass. So mass can be obtained in here. 5,000 pounds. Each column has a moment of inertia. This is given for us, so we do not want to bother ourselves to go to the I or wide flange charts to obtain the inertia. It is given for us. And a section modulus S equal to 1 over C, 17 inch to cubed, and E, we're talking about steel, 30 times 10 to the power 6 pound per square inch. Okay, so these are like important keywords you need to, whenever you read the example or whenever you read the problem, your eyes should always be attracted to specific words here that is going to give you guidance for the solution. Okay, guidance for the solution. Okay, let's clean up here and let's move on. Okay, so now we knew everything about this example, and we want now to know what are the requirements for us. Okay, now the requirement is determine the maximum response of the frame to a rectangular impulse. So we are talking about rectangular impulse, something like this. We have here t, we have here f of t, okay, and this is rectangular impulse. of amplitude. So the word amplitude here is important, keyword for you. 3,000 pounds. So we are having 3,000 here. And duration TD equal to 0.1 second. So we are having 0.1 second here. So this equal to TD for us. Applied horizontally to the top member. Horizontally means that the force is being applied in this direction. So our force is being applied in this direction to the top member of the frame. The response of interest, the response of interest is horizontal displacement. That's important because we are talking about the horizontal displacement. We're not going to talk about any vertical. Okay, so that's important issue also. The horizontal displacement at the top of the frame and the bending stress in the column. So we need two things here. We want the horizontal displacement, which means what? Exactly, U. Okay, and in the same time, and the bending stress in the column. Okay, and remember that we are talking about what? Maximum. Determine the maximum response of the frame to rectangular impulse, blah, blah, blah. So we are talking about maximum. So we need to know U maximum. And we want to know the bending stress, which is maximum going to result from this U maximum differently. So we do not disturb ourselves what is the maximum moment. Just if we could obtain U maximum, by default we're going to apply it for obtaining the maximum moment. Okay, clean everything and let's go and move on. What is the steps of the solution here? First of all, we need to, the solution steps here, we have like three different steps that we want to keep in our mind. First of all, we need to obtain T, which is the natural period of the system. Why? Because we want to get T d over T. Remember that we have, if you remember, we have the relation in the graph that we were talking about a few minutes ago. We were talking about RD maximum in the vertical axis and TD over T in the horizontal axis. So our strategy is that we want to obtain the value of TD over T here, and then we are going to get RD maximum directly without any kind of derivation or integration or these kind of stuff that we have explained in the derivation of the equation. RD maximum is going to make our life much easier. So we're going to get this value, and after obtaining this value of the RD maximum, we're going to the next step, which is obtaining maximum displacement, which is going to be U maximum, right? Because we have RD maximum, it equals to U maximum over U static node. What is U static node? We know it. It is going to be F node over K. F node, it is the maximum amplitude of the force, already given for us here, 3000. K, it is the stiffness of the system. Stiffness of the system is easy to be obtained as long as we have columns, which is fixed at the bottom, fixed at the top, because it is rigid beam connected to it at the top. So if we got RD maximum from the graph using TD over T, and we know U static node, which is obtained from the magnitude, the maximum magnitude of the force and the stiffness of the system, we can obtain U maximum easily. What is the meaning of U maximum? It is the maximum dynamic response, displacement. We're talking about displacement. Then, after obtaining the maximum displacement, we can obtain the maximum bending stress, which is in step number 3. The maximum bending stress is going to be M equals to 6EI over L squared times the maximum displacement, U maximum. This is the flow of the solution. Okay, so this is an important strategy for the solution of such kind of problems in general. Okay, let's clean up and let's move on for the detailed solution. First of all, we need to obtain, as we said, the natural period of the system. Natural period of the system. Whenever we talk about about natural period, remember always that t equals to 2 pi radical of m over k. Okay, so we have always relation between m, the mass, k, stiffness, t, natural period. If I think that all of us like memorize this very well. Okay, or we say that omega squared equal to k over m, for example, right? So in this case, if we know this very well, this means that we need to calculate k, which is going to be, because we have two columns here, right? And they are connected to a very rigid beam, right? So this means that we are having two columns that is fixed, top and bottom, right? So we have 12 EI here, it is going to be I for this column and I for this column. So we have 2I over L cubed, which is the height of the column. Okay, the height of the column, it is given for us 15 times 12, which is the conversion from foot to inches. And then 12 EI, we're going to substitute. This is E and this is I. Okay, with the calculation, we can obtain our K. Take care of the units, it is pounds per inch. And then for M, we know that our weight, this is the weight. Take care, it is the weight. Weight means that force. It is going to be divided by the gravitational acceleration, okay, pound per square inch. Sorry, it is going to be inch per square second, 386, okay. Then we're going to obtain this value, and this is the units of the mass. Take care of the units, pounds, second squared, and inch. And then the last thing is t, which is 2 pi radical of m over k, right? So we are going to get the radical of this, and then we get the value of our t. So we obtain this t, we know it, and we know td, right? Given to us already. Then let's go to the next step. Clean here, and then we're going to obtain the maximum displacement. The maximum displacement. Okay, maximum displacement. This maximum displacement is going to be from the graph, of course. Okay, we are having our graph, which is something, remember, something like this. I'm going to show it in the next slide. So we have TD, it is 0.1 over T, which is already given, or already we have obtained it from the previous slide. So we have 0.408. So we need to obtain RD maximum here. Okay, so let's clean and go down. Yes, 0.4, remember that 0.408, so we have here exactly. So here we have TD over T, 0.4, this is 0.408. Then we are going up, striking this line, okay, and then we're going to obtain the value of, this is RD maximum, because this is the response spectrum of the rectangular loading. Take care, we are talking about rectangular loading. So it is 1.2. What is the meaning of 1.9? This means that U maximum dynamic over U maximum static equal to 1.9. This means that our dynamic response is going to be almost double our maximum static response. Okay, almost double of it. Okay, so in this case, we are going to find that our RD maximum is going to be 1.9 from the figure. This is the figure that I have from the textbook. It's Mario Paz. And U static, it is known for us. F node, which is 3000 given already in the example. K, it is the stiffness of our system. Take care, it is the two columns. So it is 8,544. Then the maximum static is 0.3511 inches. U maximum, Take care. This is dynamic. However, this one is static. Both of them are maximum. This is maximum and this is maximum. Okay? Take care. So we are going to multiply 1.9, which is the maximum deformation response factor, by the value of the maximum static response. We're going to obtain 0.667. 0.667. As you can see, it is almost double of it. Okay, now let's go to the last part, which is after obtaining this Umax, we are going to obtain the maximum moment, right? Okay, now this is the last slide, maybe. It is here the maximum bending stress, the bending moment M in the columns is given by 6EI over L squared times U maximum. This is the piece of information that we want to add here. 6EI, we know Young's modulus, inertia known, L, it is known, 15. Everything is known here. All of these values already we know it, right? U maximum, it is the missing puzzle for us. Already we have obtained it from the previous step. Then we are going to multiply and get, this is the value of the moment. Okay, this is the value of the moment. Sorry, the value of the moment, yes. 265,420 pounds-inch. Then the maximum stress, because we are interested in the stress, not the maximum moment. Already it is required, the maximum stress is going to be equal to M, the moment, over the section modulus. In the beginning of the example, okay, already written, or already in the example already, it was given for us. It was 17, if you remember, the section modulus of our system. And based on that, we are having 15, okay, 15,083 pound per square inch. This is the maximum stress in the columns. Okay, if you look to the effect of bending, the dynamic load on the bending stress, you're going to find that it almost doubled, right? Almost doubled. So if you, because of what? Yes, because of this one, 1.9. So it is doubled. If I were like a designer, for example, I'm going to think twice about this, and I'm going to say, well, if it's going to be like double, I need to like reduce TD over T. I need to go here, for example, look to 1, for example, here. This means that I need to change my natural period of the system, if we say, to be giving a value of, let's assume, 0.17, for example. Okay, so that's the case here. Okay, I think this concludes everything for today's video. Thank you very much for listening to me, and I hope that you understand or you have understood well the application for the general or arbitrary general loading on a single degree of freedom system. And I'm going to, next time I will start with another thing related to multi-degree of freedom system, which is a new topic and very interesting topic. And I hope that we can, based on the information that we have gained up till now for the single degree of freedom system, we're going to use it in understanding multi-degree of freedom system. Thank you very much, and see you in the next video.